Welcome back to my channel. So today we're going to be talking about solving systems of equations using a method called Gaussian elimination. So note that this video is going to focus on putting our system into the format of an augmented matrix and then doing Gaussian elimination until we get to something called reduced row echelon form. So there are a lot of different versions of quote elimination, and I just wanted to be specific as to what we're going to talk about in this one. So let's review what a system of linear equations is going to look like. And this video is obviously going to focus on linear equations. We'll focus on 3 equations, 3 variables, but this method can be generalized to any number of linear equations in any number of variables. So let's take a look at our first system here. Our system is x minus y plus z equals 0. And our second equation would be 2x minus z equals 5. And our third equation would be 3x plus y minus z equals negative 2. So that is in system form. And we can take that system and, using our matrices, express the same information with an augmented matrix. So let's label it. So how it goes is we pretty much drop out the x, y, and z, and each row corresponds to an equation, and each column corresponds to the fixed variables. So you want to make sure that once you establish your first column, that should be where all of the x's are. Your second column is all the y's, and the third column is all the z's. The fourth column is your numbers. So our first row is 1, negative 1, 1, 0. Our second row would be 2, 0, negative 1, 5. And our third row would be 3, 1, negative 1, negative 2. One thing to be careful about is notice that when we are missing a variable, we will still have a number in our augmented matrix. That number will just be 0, which is the coefficient of that missing variable. Okay, so Gaussian will likely be new for everyone if they're in a pre-calculus class. It's unlikely you've talked about it in algebra. Okay, so let's talk about what we're going to be using our facts for simplifying and basically trying to solve these systems of equations. So the first fact is that when we take a system of equations and we scale a row by multiplying by a number, you will not change the system, even though you will change what it looks like. We call that an equivalent system. So for instance, if I take my system, let's take my original system here. Okay, so there's my system. Okay, and let's say that I scaled that up. Let's say I scaled up row 1. The way that we would write doing that is we'd put something like what we're multiplying by. So I'm going to multiply my whole top equation by 2. What I would end up getting is I'd end up getting 2x minus 2y plus 2z equals 0. And the other equations would stay unchanged. We can use a little arrow to say that we've changed it. Now notice that this system that we just produced, it has only a top row that looks different. So the first equation is different, but it's going to have the same solution as the original. Okay, that's what it means to be equivalent. Okay, the next fact that we're going to use quite a bit of is that when we add and subtract 2 rows and replace one of our equations, we'll produce an equivalent system. So again, let's take our system. So there's our system again. And let's say that what we're going to do is, let's say we take row 1 and we add row 2 to it. So our new system would be adding row 2 to row 1. We'd get x plus 2x is 3x. Negative y plus 0 is negative y. Positive z and plus negative z is 0. So we'll leave a space there. And then 0 plus 5 is 5. Okay, all the other equations stay the same. And you'll notice that with that particular choice, we actually eliminated a variable. Notice that we eliminated the z. We're now missing a z in that top equation. So if we can do this strategy systematically, we'll be able to take our system that has a lot of variables and gradually reduce it to a format that's very easy to see the solution. So that kind of tips my hand at where we're headed with this. We can do a combination of 1 and 2 at the same time. So what we can do is we can say, well, I'll take my original system. Let's take the original system here. And let's say that we want to add, let's take row 1 and we'll add 2 times row 2. So we're doing a combination of scaling row 2, and then we're going to add that new equation to row 1, but we're going to do it all in one step, because it's not too bad to do that in our mind. So how we're going to do this, so let's use I'll highlight each entry. So we're going to take our x in row 1, and we're going to add 2 times 2x. So we're going to have x plus 2 times 2x, and then for our second entry we'll have negative y plus 2 times 0 and then we'll have positive z plus 2 times negative z, and then we'll have 0 plus 2 times 5. Okay, and then all of our other equations stay unchanged. So you can see why it's easy to make a mistake here. We just had to do a lot of arithmetic, and if we're not careful to line things up and be very systematic about what we're writing, it's very easy to make small mistakes. So before we would actually continue with this process, we'd want to simplify this. So we'd want to actually compute this. We'd have x plus 2 times 2x, that would be 5x, and we'd have negative y plus 0, so it would be negative y, and then we'd have z minus 2z, which is negative z, and then that would be equal to 0 plus 10, which is 10. Okay, so that would be our new equation 1. Okay, and I'll give a little bit of more information about how to write this more concisely, because remember, we're not going to really be using our full system. It's kind of messy to write all of this. Hopefully this example really shows why using those matrices can make this visually a lot cleaner and a lot more simple, as well as give us the opportunity to use technology, which is something that I think everyone's going to be pretty excited about after they've done a certain number of these by hand. Okay, so let's talk about what the goal is with doing all of these steps. So you can already tell by when we added 2 rows and eliminated a variable, basically what we're looking for is we want to get to a system that's super easy to see a solution. So what that is called is reduced row echelon form. RREF is what it'll be called in many places. So reduced row echelon form, abbreviated as RREF, and calculators can do it, which is pretty awesome, and I'll talk about that in another video. So for now, let's take a look at the 3 kinds of solutions that these systems can have. There can be one solution. So how are we going to be able to tell a one-point solution? Let's pay attention to our simplified system. So there's ones on the diagonal, and then there is zeros everywhere else in the off diagonal. And then we'll have numbers. Okay. A, B, C. And maybe they're 0, maybe they're not, but they're numbers. Okay, compare that to what it would look like for a system to have no solution. When we do this process of eliminating, what we'll end up getting is something that looks like, check it out, the most relevant piece is this piece right here. So we have a row of all zeros, but then we have some number C, and note that this C is non-zero. Okay, so if we get a non-zero number in the bottom row and we have a row of all zeros, we get no solution. So furthermore, if this row is anywhere, so in row 1, 2, or 3, if that row is anywhere, then there will be no solution. The last thing is that we can have infinite solutions. So compare the difference. In the last row, you'd get all zeros instead of having some non-zero number in the final column. And I leave stars in all the entries on these last 2 because you might have any combination of things going on, but that last row will distinguish the difference between the two of them. Okay, so this video is going to focus on solving one of these systems that has one-point solution, and in another video, I'll talk about no solution and infinite solutions. So let's solve the following system. Our system is 3x plus 2y minus z equals 6 for the first equation. Then we'll have negative 2x plus 2y plus z equals 3 for our second equation. Then we'll have x plus y plus z equals 4 for our third equation. So let's start this process by writing our augmented matrix. So I have 3, 2, negative 1, 6, negative 2, 2, 1, 3, 1, 1, 1, 4. Okay, just make sure that we copied that down right. You'd be amazed at how many times the mistake is in the very first step, copying things down. Okay, so now is a good time to notice that these equations, it really doesn't matter what order you listed them in, it's still the same system. So if, for instance, you think that it would be particularly easier to rewrite the order of the rows, that's something you can do. And I'm going to choose to do that. It won't be clear immediately, but you'll see in a second why we would do that. I'm going to switch row 1 and row 3. Still the same system, but it's going to be a little bit easier to work with. Okay, so same system. Now what I'm going to do is I'm going to start trying to eliminate entries to get as many zeros on the off diagonal as I can. And I'm going to be really systematic about the order that I'm going to go in. So let's highlight the order we're going to do this. We're going to go first getting rid of this negative 2 and 3. And what we're going to do to get rid of them is we're going to use this 1. Okay, then the next step will be we'll get rid of whatever's on the top and bottom, and we'll be using the diagonal to do that. And then lastly, we'll be getting rid of whatever's in the third column using what's on the diagonal in the third row. Okay, now we're being very systematic in order. I'm trying to use color to suggest that. So we're going to start on the left and work towards the right, and we want to be systematic about it. Otherwise, you might have some chaos that ensues. And again, there's a lot of different ways to do this process of eliminating. As long as you're scaling rows and adding 2 rows to each other, you can do things in any order you want. But if you're struggling seeing what's fastest, being systematic about it can actually be faster because you're spending less time undoing progress that you made, basically. So I'm going to coach doing it this way where we work from left to right and are just very systematic about it. Okay, so first thing we're going to do is we're going to get rid of that negative 2 and 3. And let me clean all this up. We'll re-emphasize that as we go along. Okay, so we're going to get rid of that negative 2 and 3 using the 1 on the top row. And I'm going to be thinking about adding row 1 to row 2 and row 3, but we're going to try and use some multiple of row 1 to do it. So if I want to get rid of a negative 2, what I want to add to it is a 2, because negative 2 plus 2 would be 0. So if I want to add 2 to it, it looks like I would need to scale my top equation by 2. So I'm going to take row 2 and add 2 times row 1. And for the third row, if I want to get rid of a 3, I should subtract 3, which would be the same as multiplying the first equation by negative 3 and adding, or that's the same as just subtracting 3 times equation 1. So we'll write it minus 3 times equation 1. Okay, now this is the part where scratch paper might be very useful to you. I have the benefit of working on a tablet, so I can erase my scratch work, but I'll do a little scratch on the bottom here, and then we'll clean it up. Okay, so if I take my first equation, I have 1, 1, 1, 4, and 2 times my second row would be, or 2 times my first row would be 2, 2, 2, 8, and I'm going to be adding to that negative 2, 2, 1, 3. What I get is 0, 4, 3, 11. Just making sure I did everything right. You always want to check as you go along on these. Okay, so that is our new row 2. 0, 4, 3, 11. Okay, now let's delete that. Let's do the third row minus 3 times the first row. So 3 times the first row is 3, 3, 3, 12. Let's give myself a little bit more space there. And remember, we're subtracting that. And what are we subtracting that from? We're subtracting it from row 3. So we're taking the third row, 3, 2, negative 1, 6, and we're subtracting off the first row times 3. So that would be 3 minus 3, 0, 2 minus 3, negative 1, negative 1 minus 3, negative 4, and 6 minus 12, negative 6. And that is our new row 3. Okay, and we did not change row 1 at all. So row 1 is still the same. So that's kind of cool. You see how we have the 2 zeros where we wanted them to be? Check. Okay, so the first column is done. Now for our next step, we'll get rid of this one and this negative 1. And we will want to use our middle entry. Okay, so at this step is where people are going to tend to make a lot of different decisions. Let's clean this scratch up. So I see 2 choices. Some people are going to say, okay, I'm going to leave the order of equation 2 and 3. I'm going to leave that order exactly the same, like I'm not going to switch them. And the other half of people will say, well, I think it might be easier if I switch row 3 up into row 2. Because then I can see a little bit easier. Like if I'm going to multiply row 2 by something, I'd rather multiply that negative 1 than multiply the 4. So either way is going to be fine. You can do it either way. Just pick a way at this stage, basically. So I probably think the easier way to do this would be, I think switching the 2 would be the easiest. So I'm going to switch, because I would rather have a negative 1 there. So 1, 1, 1, 4, and 0, negative 1, negative 4, negative 6, and 0, 4, 3, 11. Okay, why would that be easier? Okay, now I get to use a negative 1, and what am I trying to get rid of is this 1 and this 4. So what I'm going to be doing is adding some multiple of row 2 to row 1 and row 3 to try and get rid of that 1 and 4. So if I want to get rid of a 1, I should subtract 1. So that would be the same as just adding row 2. And if I want to get rid of this 4, I should be subtracting 4. So that tells me that I want to add 4 times row 2 to give me a 0 there. Okay, so let's go ahead and do that. And I'll keep track of the scratch here on the bottom. Okay, so we're taking row 2, 0, negative 1, negative 4, negative 6, and we'd be scaling that row up. So just keep in mind what we're scaling up. Okay, so I'm going to take row 1, and I'm going to add row 2. Okay, so 1 plus 0 is 1. 1 minus 1 is 0. 1 minus 4 is negative 3. And 4 minus 6 is negative 2. So that's my new row 1. 1, 0, negative 3, negative 2. My row 2 stays the same. Okay, now we need to get a new row 3. So we're taking row 3, which is 0, 4, 3, 11, and we're going to add 4 times equation 2. So equation 2 is 0, negative 1, negative 4, negative 6. Okay, so 0 plus 4 times 0 is 0. 4 plus 4 times negative 1 is 4 minus 4, that's 0. 3 plus 4 times negative 4 is 3 minus 16, so that's negative 13. And then 11 plus 4 times negative 6, that's 11 minus 24, which would be negative 13. Cool, so we can see that we got the zeros where we wanted them. Perfect, that's the goal. Okay. So for the last step, we want to eliminate this negative 4 and this negative 3. And at this point, if you think about switching rows, we're kind of at the last step. There's not a lot of flexibility in terms of switching rows here because we have zeros exactly where we want them. And if I go switching rows around, I'm going to reintroduce numbers in my 0 position. And I don't really want to do that. So at this point, I'm going to be working with this negative 13 here. Unless I can see that negative 13 multiplying these numbers, they're going to get pretty big. I do notice that I can scale that last row by multiplying by negative 1 over 13, aka dividing by negative 13. I can transform that equation into something a little easier. So let's do that. Negative 13 over 13, negative 13 is 1, and negative 13 over negative 13 is 1. Okay, so now I have a 1 there, and I am a lot happier about that 1 because I can see a little bit easier how I'm going to be eliminating the negative 3 and the negative 4. So what would I have to add to the negative 3 to get 0? I'd have to add 3, so that would be plus 3 times equation 3. And then what would I have to add to get rid of that negative 4 would be I'd have to add 4, so that would be like adding 4 times equation 3. And hopefully at this stage you can see why it's nice that we're working with a 1 there. If we were working with a 13 or a negative 13, we'd have to multiply by some fractions here to get what we wanted, and that's usually everyone's least favorite way of going about it. Okay, so keeping that in mind, we're going to take equation 1. So equation 1, and we're going to add 3 times equation 3. So 3 times 0, 0, 1, 1. Okay, so 1 plus 3 times 0 is 1 plus 0, 1. 0 plus 3 times 0 is 0. And negative 3 plus 3 times 1 is 0. And negative 2 plus 3 times 1 is negative 2 plus 3, which is 1. Okay, so then rewriting this, our new equation 1 is 1, 0, 0, 1. Okay, now moving on to our second equation. We're taking our old equation 2, 0, negative 1, negative 4, negative 6, and we're adding 4 times equation 3, which is 0, 0, 1, 1. Okay, so 0 plus 4 times 0 is 0. Negative 1 plus 4 times 0 is negative 1 plus 0, which is negative 1. Negative 4 plus 4 times 1 is negative 4 plus 4, which is 0. And negative 6 plus 4 times 1 is negative 6 plus 4, negative 2. That is our new equation 2. Looking at row 3, it's the only row that remained unchanged in this step. And we are pretty darn close to having our reduced row echelon form. The only thing that's a little nitpicky about this is that we don't have a 1 on the diagonal, we have a negative 1. But if we divide that row by negative 1, we can get the one that we want there. Okay, check it out. There's our reduced row echelon form. Okay, we have 1s on the diagonal, check. Ones on the diagonal, good. And then we have our zeros on the off diagonal. Perfect. That is reduced row echelon form. We have one solution. And let's look at what our system represents. Our first system of equations, putting the x, y's, and z's back in. Remember, this was the numbers. So this would represent 1x plus 0y plus 0z equals the number 1. The second equation would be 0x plus 1y plus 0z equals 2. And the third equation will represent 0x plus 0y plus 1z equals 1. So it looks like our solution is 1, 2, 1, and you can see why that's really easy to read when you have the reduced row echelon form. Okay, so there the process is by hand using Gaussian elimination, and stay tuned for some more videos that detail what it's going to look like when we have a solution with infinite solutions, what it's going to look like when we have a system with no solutions, and how we can use technology to put an augmented matrix into reduced row echelon form. So in other words, how do we use technology to expedite the process that we just did? See you next time.